Hi, my name is Andrew Chabot, and this video is going to be about the SHA3 256-bit visualization created in the hash function visualization language. So this file loads much faster than the SHA-1 or SHA-2 files because of how simple the logic is to find where the arrows should be located. We can see here that the initial file that loads is for the sponge function overview. The sponge function is the overall construction of SHA-3 and basically tells us how our input block is taken in over multiple, we can call them runs, to get our output hash. So this capacity here and rate will be initialized to 0, and our input block will be XORed with this rate and taken in as input with the capacity to this F function here. That is actually the Keshak F1600 function. Where this function contains the actual calculations that occur for the proper hashing in SHA-3. Our output from this function is then going to be taken and placed back into capacity and rate sections. So basically, our capacity and the XOR result from our rate and input block are going to be concatenated together, the capacity first and then the XOR value next. And that will be taken as the 1600-bit input to this function. Then our output is going to be a 1600-bit block, and we'll split it up back into the capacity and rate. This split is basically just happening here so that we have something to XOR with our input to be taken in. It's not always the case that we have two different input blocks here. We could have many more input blocks if our input text is significantly longer than something that we have here. Or we could only have one if our input text is shorter. So if we only had one, you could cut off this whole middle section here. I just drew like a little square around it and simply take the rate as an input, as the output hash here. But in this example that we're using in the visualization, we will be running the Keshak F function twice. So after we run it for the second time, we'll be left with this capacity value that we don't actually use in the output and this rate value here. And we'll simply be truncating the output hash to get the result here. So I can run through this main sponge function just to kind of show what's happening. So the population of C and R are going to be initialized to 0 here. And then we're going to initialize our input blocks. This is the text that we're actually trying to hash here. So we have 128 byte input, and these are two 64 byte blocks. So we'll XOR these two together. This is pretty simple. We're just going to get, we're just going to get the same result that we get in if you XOR something with zeros. All right, so then we'll take these two as input to our, we'll just call it the F function for now here. And we're going to get these two outputs for the capacity and rate. And now we'll kind of repeat the same process where we XOR these two together. Obviously, the result's going to be much different now. And we can take a look at the sub-visualization here to see what's going on. So it's pretty simple. We're just taking in the bytes here for the rate and our input text and translating these into bits. And these take up a massive amount of space when they're bits, as can be seen here. So we'll XOR these together, and we get our result here. And this is just going to be translated back into bytes. All right, so we have this result, and we'll concatenate that back with the capacity to be input to this f function again here. Now we have that split up again into the capacity and rate. And we take this rate and truncate it to our 256-bit output. So essentially just the first 4 lines of this here become our actual output hash here. So this seems simple looking at the sponge function, but you may be wondering what's actually going on in this f function here. So that's what we're going to delve into now and look at the subvisualization of the Keshak F1600 function. All right, so here's what the main screen for this function looks like. You can see we have the round constants here, and we have the description box here. And in the middle, we have this a round 0. This is going to be our input block. We have this function called the theta function, the rho function, the pi function, the chi function, the iota function, and finally we have the a round 1 output here, which will, just like with SHA-1 and SHA-2, this will become the input to the next round. You can also notice that all of these functions only have one input going into them, which is the output from the previous function. This is true for all of these except the iota function, which takes in both the chi output and the round constant for the current round. All right, so this block is just going to be populated with the current concatenation of the capacity here and our XOR output here. So you can see this A6 value lines up and this 0E part lines up there. All right, so we will take this and this is going to serve as input to our theta function. And now the theta function, we will jump into this subvisualization. So the subvisualization for the theta function, it also doesn't get to the lowest level bit functions yet. You see we just have this description of events here. This is kind of the only place where this is able to fit. So we'll have our A bytes. These are going to be populated from the input to this function. And this is going to be the input to this thing called the C function. And this is going to be one of the inputs to our XOR loop here. But we'll start with the C function because we are going to need to run the C function and the D function to be able to run the XOR loop in the first place. Okay, so this value taken as input to the C function. Let's dive into the C function and see what's going on there. You can see now we are kind of deep in subvisualization land. We have this theta C function. Its parent function is the theta function. The parent function of that is the Keshak F1600 function, and the parent function of that is the sponge function. There's a lot more going on in SHA-3 compared to the SHA-2 and SHA-1 visualizations that previously looked at. All right, I'm just going to set this back up nicely. Okay, so in the theta C function, we are going to treat this A input block as a matrix here. And the matrix is 5 by 5, so 25 words in total in this matrix. And then for each round of the theta C function, we're basically going to be taking a complete row of this and XORing each of the individual words in that row together to get an output byte for that row. So you can see here, we're taking in, this is the first word up until EA, this is the next word up until F1, this one is the next word up until 22, next word up until 71, and next word up until the 4F there. We are going to translate this into bits. So we get these bit values and XOR them together, kind of just chaining these XORs together as we go along. So we are left with this XOR value here. This is translated into the byte value, and we are going to append this to our output here. So this is going to end up being essentially an array of 5 values versus our input is a matrix of 25 values. All right, so we will continue this process for the next row of values and chaining these XORs together and getting the byte. And you can see now it's more clear like that we're appending here. All right, so let's just skip ahead to the end here. And this is our final output here. So that's the C function. And you can see this, the output value is updated in this box for the C function. And the D function simply takes the C function as input to it. So the D function will be taking in the C function and turning it into the same size but a different sort of array. So for we're basically going in values from x equals 0 to x equals 4, and we're essentially running a for loop here. So when x equals 0 in our first round here, we're going to get the value at c negative 1, which is equal to the value of c at 4, since all of these values are being taken modulo 5. And for cx plus 1, we just get the value at 1. So you can see this is taking the second value here from CD to CB, and this one's taking the last value from C4 to 9A. We'll translate those into bits, and we'll right rotate this value here by 1 to get the result here. Finally, we'll XOR these together, get our output byte, and append that to our array down here. All right, so we'll repeat this process for x equals 1. Now this gets the first value instead, and this will get the third value at the index of 2. You can see we're just repeating same steps, and we are concatenating this to the end. All right, we'll just step through concatenating the third value, now the fourth value, and finally we're on to the last value here. This is interesting when we take the value at index 4 and add 1 to it. It becomes 5. 5 modulo 5 is 0, so we're actually just taking the first value on this side and the fourth value on this side. But same process, XOR them together, and eventually we get this output down here. And this will become our D function output. So now that we have our D function here, we're taking that at the same time that we're taking our original A block input and running them through our XOR loop. And this XOR loop is actually pretty simple. It has 25 rounds, and for each round is based on a value in the A matrix. So we'll be going row by row, and inside of those rows we'll be taking the column value and XORing it with the current D value for that row. So the first A row is when this X value is equal to 0. So we'll be doing that for 0, 0, 0, 1, 0, 2, 0, 3, 0, 4, etc. But the whole time that this X value is equal to 0, we'll be taking the same D value. So let's first populate these in, give you a better idea of what's going on. So now that we've populated these initial blocks here, we'll be taking the first row of D of X, since our X value is equal to 0 right now, and we will be taking our first entry of A. So you can see here we have this 22 to FF value here, and we're taking our first word of A here. We'll translate these into bits, XOR them together, get that byte, and append it down below to our output matrix here. So this will continue. You'll see that the X value stays the same. So we are just taking the same value that we had before on this D value here. The A value increments to the next one, which starts with AC here. And again, we XOR those together, append the value down here. So D value is still the same, but let's skip ahead 2 more rounds. And now you see we're taking the next value of D here for 44 to 25. we still are just incrementing by 1 essentially on the A side here. Again, just XOR together, take the byte, and add it to this output block down below. So we can just keep on moving through the rounds. You'll see that these just keep on getting populated, and we're running through 25 rounds. And now we have our output block here, and this is the complete output of the theta function now. And we can see our value here. Just transfer it into the theta output block, and we've now finished that theta function step. All right, so now we just exited out of 2 windows really quick there, but we are back to the Keshak F1600 function. So we're only 1 subvisualization deep now, and we can move on to taking this theta output as the row input here. All right, so let's jump into the row function now. So the row function is essentially taking in every entry in the theta block and rotating it by a set amount. These are all constants, and the constants just change based on the round. So we'll take in this first value here, this 84 word here. Translate that into bits. We'll look at our current rotation table and get this 0 rotation. So this one shouldn't change at all, and we expect to get 84 here. And that just gets appended to the output block. So next we're taking in the 8E word, translate that to bits, take our rotation amount from the table, and now this is 36. So this one will have a much more pronounced change, and we get our output here. And there we go. Next, we're taking in the 71-bit, and we can look at our table, see that we're going to shift this by 3 bits to the right. So you see these 3 ones have now moved into this position here. All right, so this just repeats on and on for 25 rounds. And that essentially is the row function there. So we're just like we did with the theta to row function transition, we're going to do the same thing with the row to pi transition. So we're taking the output of row and taking that as input to pi. So the pi function is rearranging where certain bytes are from the row output based on just this formula here, 2x plus 3y. So the current y value was previously the column number, and the x value is the previous row number. But now the y will become the row number, and this equation will dictate the column number. So we can see here, these are our this is our input block here. So let's take the first bytes here. And you can see we're in row 0, column 0. So all of these values have been populated with their correct 0 values. So we'll run through this equation, but it's just going to be 0 for this first value, so not very interesting. And you see this one just we'll take the 0, 0 as input, and it will be placed here in the output matrix. So next we're taking in this 43 8a word, and this is located at column 1. So the y value here is 1, the x value is still 0, but we actually have interesting values to play with here now. You can see we plug into this equation, we get 3 mod 5 is still 3. So we're going to be placing this at row number 1 and column number 3. So that gets placed here. All right, so next we have the third entry from our input block, and now the column number will be 2. That means that the output of the 2x plus 3y equation will be 6, and 6 mod 1 is 1. So our column is going to be 1 and our row is going to be 2. And we'll place this at this location. So this is just going to repeat on, and the way this function is set up is that all of these will be properly populated with an input block. They'll just be rearranged except for the first block. So let's just keep on moving through, and we can see that eventually we are completely done, and this block has been populated fully. And that will be the pi function output. So we take this pi function output, and now we're going to input it to the chi function. So the chi function, let's just populate those bytes right away. And this is kind of a little bit more similar to just some normal bit functions, except we're taking multiple parts of the input to rearrange and create an output. So we're going to take the first byte right away, but then we'll also take the first entry in the next row as well, and the first entry in the next row as well. So you can see this one's the 8484 value. This 7F is right here, and this 691 is right here. So we'll translate all these to their bit values here. We'll take the not of this middle one to get this value. We'll AND that together with the right value here to get this value, and we'll XOR that with our first value here. That leaves us with this bit. Translate that into a byte as per usual, and we're just going to append this to the matrix. As per usual too, with these operations on the matrix where we're accessing certain values, these will be taken with respect to 5. So if it's a 6, it will become a 1, etc., etc. So we can keep on moving through the rounds. This will fill up pretty quickly here, and we finally get this output. All right, so now that we have that output, we want to populate this round constant over here with the current round constant. And for round 0, that's just a 1 value. So it's time for the simplest function here, which is the iota function. So we'll open this up. You can see we have, it looks a little bit confusing at first, but it's actually really simple. We have the inputs here are the chi output bytes and the round constant bytes here. So we'll populate those. We're going to take the first value in this slot here, and the rest of the values we'll just use here and kind of save for later. All right, so we'll just take in the bits of that round constant and the bits of the first word here, and we'll be XORing them together to get this bit value. We'll take the byte value of that, and all we're doing here is taking this value and just concatenating this value onto it. So that leaves us with, you can see here, and this is still the first block, or sorry, the first word, and this is the rest of the input block. All right, so now that we've looked at the iota function, that is all of the functions that occur within a round of Keshak F1600. So that leaves us with this output down here for round 0 of Keshak F. And just like we did with SHA1 and SHA2, this value is going to be the input to the next round. So we'll populate that up there. You can see now we're on round 1. The round constant is going to change in between the rounds, and that's the only thing that changes here. So you can see we'll just we can just run through it here one time, you know, without jumping into all of the functions again. So this theta output becomes the input for rho. Rho goes to pi, pi to chi, chi to iota with a round constant. You can see everything stays the same except for this first word, and that's the output for round 1. That will become the input for round 2. So we can continue to step through here, and this Kashak F function is run for 24 rounds. So this is our final output value from those 24 rounds. And this output here, the first 1088 bits are split back into the capacity here. And the next 512 will become the rate. So now that we've run through that, we can return to this, our main sponge function overview, back to its parent function. So we already looked at this before, but we'll take the rate here and we'll just truncate it to this value, and that will be our final hash output. So this has been the presentation of SHA3 256-bit in the hash function visualization language. Thank you for watching.